Hi everyone, welcome to topic 6.1, testing a claim or idea with one sample hypothesis testing. Here are the learning objectives. First, I'll discuss how to generate research questions and hypotheses for these questions. I'll then go further to discuss the null and alternative hypotheses. Next, type 1 and type 2 errors will be differentiated and linked to alpha levels. I'll then describe two methods for conducting hypothesis tests, the p-value approach and the critical value approach. I'll then use a step-by-step method to go from hypotheses to decisions. Okay, so first let's distinguish between one sample and two sample tests. Please note, two sample tests will be discussed in topic 6.2 onwards. So for a one sample test, we are comparing our sample mean to our hypothesized population parameter, which I often think about as being a benchmark value. For example, is the average commuting time to work less than 32 minutes? Is the average weight of a potato chip bag equal to 80 grams? Is employee engagement scores for an organisation above the industry average of 7 out of 10? As you can see, these examples only involve the collection of one sample of data, the calculation of a sample mean, and then this is compared to a benchmark value. This is different to two sample tests or match paired tests. Research questions for these tests are more along the lines of, is there a gender pay gap within our organisation? Is the weight loss program effective, i.e. looking at before and after studies? And these will be discussed in topic 6.2 onwards. Okay, so with our hypotheses, these are written in pairs. There is a null hypothesis and an alternative hypothesis. The two hypotheses are exhaustive, and what we mean by that is they're exact opposites. And for the research question about time to complete a piece of work, the null hypothesis would be HO : mu equals 25 minutes. Note that the hypotheses are always about the population parameter and not about the sample, as we know all about the sample mean because we've collected sample data. But what we're doing is we're using those sample statistics to understand the unknown population parameters, as is the way of inferential statistics. So we always begin with the assumption that the null hypothesis is true. Often, but not always, the null hypothesis refers to the status quo. It always contains the equal sign, and this may be less than and equal to or greater than and equal to. It may or may not be rejected, but it is never, ever accepted. When it's rejected, this is because there is enough evidence to reject the null hypothesis, but without enough evidence to reject it. This does not mean that we have enough evidence to accept it. The alternative hypothesis is the opposite of the null, and it's often easier to write this one first. For the research question about the average time to complete a piece of work, the alternative hypothesis would be HA or H1 : mu does not equal 25 minutes. The alternative hypothesis never contains the equal sign, but instead will contain a not equal to sign or a less than or a greater than sign. If we have enough evidence to reject HO, we will then conclude with H1. So in this example, we would conclude that the average time to complete the piece of work is not 25 minutes. Okay, so in formulating hypotheses, I don't recommend you focus on the status quo because sometimes that can be a little bit confusing. To help you understand this, think about the last example on the previous slide. In this example, because we're interested in a difference, that is, the time to complete a piece of work is different to 25 minutes, our hypotheses contained the equals and not equals to signs. If, however, we wanted to test whether the time to complete the work is less than 25 minutes, this is referred to as a directional test. In this case, the alternative hypothesis will contain the research question, that is HA : mu less than 25 minutes. And the null would be HO : mu greater than or equal to 25 minutes. In this case, working out the hypotheses by considering the status quo really doesn't work. On this slide, you have other ways to work out the hypotheses. As you can see, we might be considering whether a bag of potato chips has on average 80 grams as stated on the packaging. In this case, we're testing the status quo. We would test this as a non-directional test with equal and not equal to signs, as we really are concerned with, avoiding underfilling or overfilling the bags. Obviously, underfilling misrepresents the packaging, and overfilling leads to wastage and reduced profits. In the second example, a tyre company may want to test whether their tyres last longer than 60,000 kilometres. So, then they could use this information for advertising. The 60,000 is the industry figure, maybe an industry figure or a figure from laboratory testing, or perhaps an expert opinion. Either way, we are testing a research hypothesis where the research question is stated as the alternative hypothesis, and the null hypothesis is the exact opposite. Now at this point I should stop and say that you're probably thinking the hypotheses are the wrong way around. Please note this is very common when I teach this lecture face to face, but over time and after doing multiple examples you'll come to understand that this is the only way these hypotheses can be presented. Think about the burden of proof. The only way to prove that the tyres last longer than 60,000 kilometres is to state this in the alternative hypothesis, as we never accept the null hypothesis, only the alternative. Lastly, we have another directional test where the average wait time is hypothesised to be less than 15 minutes. Hence the alternative hypothesis includes this claim about the population. So with hypothesis testing we make one of two decisions. We either reject the null hypothesis or we do not reject the null hypothesis. Please note we never accept the null hypothesis, as we can never know the true state of affairs. We only reject it if we have enough evidence to do so, and when we reject it we can only conclude the alternative hypothesis, because this is the exact opposite of the null. Here are the three main steps to hypothesis testing. First, determine whether your test is about the population mean or the population proportion. In this course we are really only discussing the population mean, but once you understand this you can easily apply this method to the proportion data. Next you decide whether you are conducting a directional or a non-directional test, that is a one or a two-tailed test. Lastly, you need to set up your hypotheses. As you can see on the slide, the null always contains the equal sign and the alternative never does. Okay, so here's an example for you to work through on your own. A trade group predicts that the back-to-school spending will average $606.40 per family this year. So step one, the parameter of interest is mu, the population mean. We're conducting a non-directional two-tailed test as we're interested in is there a difference in spending to this figure of $606.40, and the hypothesis is stated as HO colon mu equals $606.40 and HA colon mu does not equal $606.40. So now it's your turn. Please pause the video and develop hypotheses for the two different research questions presented on the slide. When you're done, press play and I'll go through the answers. Okay, so to test the research question, is the average back-to-school spend less than $606.40 per family? The null hypothesis is mu is greater than or equal to $606.40, and the alternative hypothesis, which is often easy to write first in this case because it contains the research question, is mu is less than $606.40. Well done if you got that correct. Next, to test the research question, is the average back-to-school spend more than $606.40 per family? The null hypothesis is mu is less than or equal to $606.40, and the alternative hypothesis is mu is greater than $606.40. Okay, if you got both of those exercises correct, you're on your way. Well done. Okay, so here's the bonus question. Try this one out. Again, press pause and see if you can write the hypotheses correctly. The correct hypotheses are HO colon mu equals 32 minutes and H1 colon mu does not equal 32 minutes. This is actually quite a difficult question where we will never truly be able to prove the politician's statement, surprise, surprise. We will only be able to disprove or reject it if the sample evidence shows that the mean is significantly different to 32 minutes. Think that through a little bit more. If there is evidence that the mean commute time is different to 32 minutes, and then it's actually found through further testing to be significantly less than 32 minutes, this would delight the politician. But on the other hand, if the mean commute time is found to be significantly different to 32 minutes, and then through further testing is significantly greater than 32 minutes, the politician may not be happy. Then the reality is that if we do not reject the HO in this case, the conclusion would be that there's not enough evidence that the average commute time is different to 32 minutes, which clearly does not prove the statement but does not reject it either. So now that you're all experts on formulating hypotheses, let's work through a visual example of hypothesis testing. First, let's take commute time, that example. In this case, the null hypothesis was HO colon mu equals 32 minutes. We then determine our population, in this case all motorists living in the metropolitan area of Perth and commuting to work by car to the CBD. After defining the population, we then randomly select a sample and compute sample statistics. Suppose that the sample mean x bar is 20. With hypothesis testing, we are considering whether a sample mean of 20 is likely given a population mean of 32. In this case, we will determine that it is unlikely and reject HO. it is more likely that the population mean is closer to the sample mean of 20. Here is this example using our sampling distribution of the mean. As you know from previous topics, the mean of the sampling distribution is equal to the population mean, and the distribution is normal, well above certain sample sizes. See your central limit theorem slides. So with this in mind, it is unlikely but not impossible to get a sample mean of 20 if the population mean is 32. And in this case, we would reject HO on this premise. Okay, so how close is close enough? What do you think? We have to allow for some error in our sample mean due to sampling error or differences from sample to sample. So if we compute a sample mean of 30, does the statement about the population mean of 32 still hold true? I can hear you say probably yes. So then that means that a mean of 34 would be okay too, right? So where is the point where the sample mean is too different to support a hypothesized population mean of 32? Maybe below 24 minutes and above 40 minutes? Maybe you are more stringent than me, or maybe less stringent. There's certainly a grey area here in this example, as we are simply just thinking about the exercise without being confused by the statistics. Please note, however, that with statistics there is an exact cutoff that is calculated and applied, so rest assured there's no grey area when we are making decisions about hypothesis testing. In making decisions about the cutoff, you need to consider your alpha level as type 1 and type 2 errors. How much type 1 will you allow? Generally in business research we allow 5%, so this means 5 times in 100 will make a type 1 error. Or in other words, we will reject the null hypothesis when the null hypothesis is true and should not be rejected. We will not know when we make this error, however. On the flip side, 95% of the time we will make the correct decision of rejecting the null hypothesis when it's false and should be rejected. You may ask, well, why not change alpha to 1% and reduce type 1 error even further? Well, the problem with this is that we increase type 2 error of not rejecting the null hypothesis when we should reject it. So it's a fine balance. In management research, an alpha level is normally set at 5%, and this is the norm and the value used through this course. Here is a table that usefully points out type 1 and type 2 error. As you can see, when the decision is to reject the null hypothesis and the null hypothesis is true, this is type 1 error. Then when the decision is to reject the null hypothesis and the null hypothesis is false, this is a correct decision. Then when the decision is do not reject the null hypothesis and the null hypothesis is true, this again is a correct decision. Then lastly, when the decision is not to reject the null hypothesis and the null hypothesis is false, this is type 2 error. I can hear you already say, how do we apply this stuff? Have a look at this slide. Here is a legal example which helps us to understand hypothesis testing and errors in decisions. In Australia, the burden of proof falls with finding enough evidence to prove someone guilty. Otherwise, they are found not guilty. If you live in a different country, this may be different. Anyway, for Australia, because of this, the hypotheses are written as follows. HO, an accused person is innocent, and HA, an accused person is guilty. In this case, a type 1 error occurs when an innocent person is found guilty by the court. And a type 2 error is where a guilty person is deemed not guilty. In Australian society, type 1 error is considered the worst, and in fact, there is a saying by Benjamin Franklin and others that it is better for 100 guilty persons to escape than one innocent person to suffer. Hence, because type 1 error is seen as more costly to society than a type 2 error, the alpha level, which is tied to type 1 error, is adjusted accordingly. Lastly, if you read journal articles, you often see researchers refer to all three standard alpha levels of 1%, 5% and 10%. Your book provides the following interpretations of these alpha levels, which I'm not overly excited about, but they do help show that a smaller p-value is more convincing. But please note, we should never say that something is very significant or marginally significant, etc. You will see this in journal papers quite a lot, and it's incorrect. Significance is about a cut-off point, and therefore a finding is either significant or not significant, regardless of how small the p-value is. This is because of differences from sample to sample, and these will yield different p-values. Lastly, we are mostly working with a 5% alpha level, and this is the golden rule. If the p-value is less than 0.05 or 5%, we reject the null hypothesis. Otherwise, we do not. This rule always holds true regardless of the test. Well done.